So this last module, which is really short, is only going to be dealing with modeling data. So I have these two pictures here, and these are quite relevant. They're current to July, the end of July 2020, and they're about the coronavirus. So on the left-hand side is the deaths and hospitalizations, and this is the 7-day average of hospitalizations, how many people are in a hospital on a specific date. And the other one is coronavirus cases by day. And in March of 2020, there was hardly any in North Carolina, and it's been growing steadily throughout. So these are two different types of models that will fit these pictures. And the one on the left is more of what's considered a linear model, where it almost falls on a nice straight line. I hate saying straight line, but it falls on a line. The coronavirus cases per day, though, is what's known as exponential. So these are the two things we're going to be dealing with in this module, is linear and exponential. And I figured I'd show you some current reasons why we might want to pay attention to this, because exponential pretty much eventually gets out of control. Uh, at this point in time, Florida and Texas numbers are going through the roof. And it took me a little searching, but here's graphs for Florida. And you'll notice that they're a little bit different than North Carolina, where North Carolina had a linear hospitalization 7-day average. The Florida one is much more what I would consider exponential, and the same thing for the daily deaths. It's kind of exponential also. So this is why Florida at the time is considered a hotspot, where North Carolina, even though the cases are growing exponentially, the hospitalizations are remaining kind of linear. So being able to recognize a graph and what it's really doing is basically really important when we start talking about modeling data. So these are the two ideas we're going to go across: linear to start with, and then exponential. So there are three types of linear models, but I've only graphed two of them here. The third type is kind of boring. It literally is nothing is changing as time goes on. Um, so you get paid the same amount of money every month for 12 months. So, it's kind of boring. It would be better if you had the graph on the left as your pay throughout a year, and it would be really bad if your pay was the green graph on the right, because then you would be losing money every month of the year. All right, so let's talk about these linear models. So the graph on the left I basically built on simple interest. So you get a little bit of money every single month for interest um, on money, and it goes up nice and steadily. The graph on the right I built on depreciation, kind of like the depreciation of a car over time. So as you own a car over the years, the value of the car is declining a little bit every year. So the graph on the left, the simple interest graph, your money is increasing as time goes by. So we consider this to have a slope that is positive. And we can think of that as increasing. And then depreciation, you're losing money on your car every year. This would be a slope that is negative, or a decreasing linear model. So these are and then the boring one where it doesn't change at all. This is called zero slope. So these are really important to understand, because slopes are what we've been dealing with all semester, that are known as rates. So these lines are built in what's known as a rectangular coordinate system, and we have generally what we call the x-axis, but it doesn't always have to be called x. Like in this case, it's really the t-axis, where t is in years. So we can always change the name of the axis and the variables we're dealing with. Generally, the vertical axis is called the y-axis, but in this case, it is, the amount of money in an account. So we can consider that the future value axis, or capital F. If we're talking about the depreciation of a car, again, we would be talking about the t-axis here, or years, that we've owned the car and it's losing money as we own it. And then again, we're talking about money here. And again, we can probably call it a future value, even though this one is going downhill rather than uphill. All right, so on these graphs, we have to be kind of careful. The axis that goes horizontally is usually called the independent axis. Independent. Because those are the ones you pick first. So you say, well, how much money will I have after 8 years? You would go to 8 years, you'd go straight up to the graph, and you'd come over here to the y-axis straight across, and you would run into an amount, it's around 17,500, and then therefore this side becomes known as the dependent. Axis. So we're going to pick numbers off the horizontal axis, and it's going to generate numbers on the vertical axis, the dependent variable. So it's really important to know which variable you're dealing with is independent, which one we're picking to generate the dependent variable on the other side. So there is what's called order to how we're going to do this. So the order that we normally choose is x comma y. The two graphs above are actually t comma f. So the independent variable is the first variable, and the dependent variable is the second one. So over here, the independent variable is time, and the dependent variable is future value. Now, we can take the variables and switch them, especially in this situation. Maybe we're curious how long it'll take to reach a future value. So then the coordinates would be switched, the future value becomes independent, and the time becomes the dependent variable. So as you're doing these problems, that is the hardest thing to figure out. Which order am I going to pick these two letters in? Because the order actually matters. So for example, my car gets 27 miles per gallon. Okay, I want to find out how many miles I can travel on a certain number of gallons of gas. So if I let m be miles and g be gallons, which variable is the independent variable? And you have to be able to pick this out really well so that you get the order of the coordinates right and you can get the answers correct for my questions. So when you're reading the information, you have the 27 miles per gallon. That's awesome. But the problem really is, Harvey, but the problem really is here. I want to find how many miles. So if you're looking for how many miles, that becomes your dependent because you're looking for it. So what you're going to be given is how many gallons of gas. So the independent variable is going to be g. So when we set up a coordinate with these things, or an ordered pair, the independent variable is going to go first, and the dependent variable is going to go second. So when I know how many gallons of gas I'm going to use, I'm going to be able to calculate how many miles I can travel. So that's pretty much how you're going to rip these problems apart. All right, so now that we have this idea of ordered pairs, independent and dependent, let's change it into a fixed system where x is always the independent variable and y is always the dependent variable. So our ordered pair is always going to be x comma y. Um, so x is usually the horizontal axis, but I shouldn't say usually, it's always the horizontal axis. and the y is always the vertical axis. And technically, they're just two number lines that intersect at what's known as the origin, where you start plotting all points. You start at the origin, 0, 0. All right, so let's talk about plotting points and then go from there. So if we have a point that is 3, negative 4, what this means is you're going to go positively in the horizontal direction. So to go positively, we're going to go right 3. And then the negative 4 is the vertical motion, but because it's negative, we're going to go down. So when you're talking about up and down, up is positive. When we're talking right and left, right is positive. All right, so then from the origin, we're going to count 3 to the right and 4 down. So we're going to go 1, 2, 3, but that doesn't generate a point because we also have to go 1, 2, 3, 4 down, and this is the coordinate way down here of 3, negative 4. Okay, and now technically, these jumps are not part of the graph. They were just me counting. All right, so there's 3, negative 4. Now, most people are pretty good with graphing um, points that are in what are called the quadrants themselves. They have a harder time when it becomes points that are on one of the axes. For instance, if I do 0, negative 5, well, the 0 means no left or right, so we're not going to move anywhere. We're going to stay right at the origin. And then the negative 5 is the second one, so this is going to be down 5. So this just goes from the origin, from the origin, we would just go 1, 2, 3, 4, 5. And since we're not moving left or right, that becomes our coordinate. And again, we can get rid of our little counting here. So that point there is 0, negative 5. All right. If I want to plot the point 6, 0, well, that means we're going to go 6 right and 0 up and down. So we're not going up and down at all. We're just going to go 6 to the right and stop. So 1, 2, 3, 4, 5, 6, and plot a point. Never count the origin as 1. Its origin to 1 is 1. Basically, you have to take a step first before you count it. And then again, we'll erase our little jumps. That's a mental thing. You should do that in your head. And then this coordinate is 6, 0. All right, now they have fancy names. Like this 6, 0 is known as a x-intercept. It is on the x-axis. And the 0, negative 5 down here is known as a y-intercept, otherwise known as on the y-axis. And you'll notice that on x-intercept, the y value is equal to 0, and on y-intercept, the x value is equal to 0. So it's always the opposite one is going to be 0. Now the y-intercept, of course, is a little bit more important later on, but the x-intercept is actually the more important of the two of them in mathematics. But we're not going to get into all that fun stuff. That's a whole nother course. So while we're talking about lines, what defines a line? So a lot of people say, 2 points define a line. So let's plot 2 points and see what that does for us. Negative 2, negative 1, just for an example. And 2, 5, so 2, 5. And sure, 2 points define a line, but the only clear line that you can draw between 2 points is a line segment. So I'd like to go beyond a line segment. I understand that most people are like, well, it continues on in the same pattern on both ends. But we really have to discuss what is that pattern. So the other way of defining a line is 1 point and this thing that's called slope. So let's talk about slope for a second. So let's let our 1 point be, let's do it in hot pink, this point. So let's say this point -2, -1 is our given point, and I want to talk about slope. Now, slope is just how I go from this pink point to this pink point. And the only things that you can do in a graph paper, this rectangular grid that we have here, is to move horizontally left and right or vertically up and down. There is no such thing as counting diagonally. So one thing we could do is we could count up. So 1, 2, 3, 4, 5, 6, and that gives us at least level with that second point. So this would be 6 up. And then from here, it would be 1, 2, 3, 4. So we would have this, basically what I would say is up 6, right 4. And that idea of up 6, right 4 is considered the slope of the line. And it's really nice to recognize, let me get rid of my little loopies here, that there are other ways of going up 6 and right 4. So another way to go would be to be going, instead of up 6, let's go half the distance, up 3. And half of 4 is 2, and look where we're landing. It's right on the line. So 3 over 2 also lands on a point on our line. So let's see if that continues. If we go up 3 from here, and then right 2, we land on the point that we started with. So this idea of slope is a ratio, and ratios come in a lot of different values. So we could go up 6 and over 4, or we can go up 3 and over 2. What if I went up, let's do it in purple, 1.5? So I would go 1 and then a half. Now that would be a fourth of 6. We're cutting it in half twice. So if I cut 4 in half, that gets me 2, and if I cut 2 in half, that gets me 1. And if I go 1 to the right, I'm on the graph again. So this ratio doesn't have to be integer values, integer over an integer. They can be fractional amounts. So I could go up 1 and over, I think it's like 3 halves, and we'll land on the same line. So that's the pattern we're looking for. We're looking for, I'm going to go with the small number, up 3 over 2. It generates another point, and we can construct another line segment. The cool thing is we can also reverse the order. Whoops. We can go down 3 and left 2, and we get a point, and that would continue the pattern of the line, and we can do that forever. So that is the power of slope. So the slope of this line we know is either 6 over 4, 3 over 2, 1.5 over 1, and we can keep going with this pattern smaller and smaller, but we also can go the other direction. We can go 12 over 8. But generally when we talk about slope, we talk about a reduced fraction. So the slope of this line is 3 halves, and one thing to notice, it's positive, and if you look at this graph, it is increasing as you move from left to right. The third way to define a line is with an equation. And all of these things that we're writing right now are all interrelated because we're talking about the same thing. So an equation of a line in standard form looks like this, and we're not going to spend any time with this one, but you'll notice that the exponents on the x and the y are both 1, so this is considered a linear equation. Now the formula that we're going to be using for the most part is either y equals mx plus b, and the cool thing about y equals mx plus b is m represents the slope, and b is the point, the one point that we're going to graph, kind of like definition number 2 here, and the point is the y-intercept. Remember, y-intercept, x is equal to 0. So these are the 3 ways to define a graph. The best way, I think, even before an equation, because you'll eventually come back to it, is a point and a slope. You may have noticed in the last video that instead of like plotting a point going left and right first and up and down second, slope is literally the reverse of that. You have to go vertically first and horizontally second. And it's not plotting a point, it is moving from one point to another point, and then you're plotting one. So when we talk about slope, I'm going to always call it change in y over change in x. And you know, mathematicians are generally lazy, so they give a symbol for change. So change in y is a triangle y, and change in x is a triangle in x. Now, the triangle, of course, is a Greek letter, but we don't have to get into that. So when you go to a grocery store and you make change, like a candy bar costs $1, you give the cashier $5, and they're going to give you change. Well, to make change, you're taking 5 and subtracting 1. So whenever you see this triangle symbol, it really means subtract the y's and subtract the x's. And the order is really important, just like plotting points. All right, so when we start looking at the change in y from one point to the other, and it really doesn't matter what point you start at. If I start at this point, my change is going to be negative because it would be going down. And when we get level with this point down here, then we'll go in this direction, and that would be positive. So it would be a negative over a positive. Conversely, get rid of that. Let's say we start at the other point. Well, to do a change in y on the other point, down here, we would have to go upwards first. So that would be a positive change in y. We'd become level with the other point, and then eventually we'd have to go in that direction, which is to the left, which is negative. So then it would be a positive over a negative, and you still end up with a negative slope. So it doesn't matter what point we're going to move from. Generally, I like going left to right, so I'll pick the far left one. So if I pick the far left one, we're going to go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get level with the bottom point. So this is down, and I just forgot how many I counted. 1, 2, 3, 4, 5, 6, 9, 10. So this is down 10, and then we're going to go 1, 2, 3, 4, 5, 6 to the right. So I'm going to put a plus 6 there. So I would say the change in y over the change in x is equal to negative 10 6, which is the same thing as negative 5/3. So that means I could also go down 5, 1, 2, 3, 4, 5, and right 3, 1, 2, 3, and that generates a third point. Makes it easier to draw my line. So my line would be there. It's not a very good drawing of a line, but it's pretty close. So that is how to find slope. Well, that's how you do it on a piece of graph paper. What if we just had the coordinates? Is there an easier way to get to negative 5, 3? Well, remember, I considered change as subtract. So if I find my change in y over change in x by subtraction, I'm going to subtract my y. So let me write my points again so we can talk about it down here. So if I'm going to subtract my y's, then I'm looking at the 3 and the negative 7. So if I'm looking at my 3 and negative 7, this is going to become 3 minus a negative 7, because to make change, you need to subtract. Over, and then I'm going to subtract the x's, change in x, which are the negative 4 and the 2, and I have to keep the order the same. So because I went 3 and negative 7, I'm going to have to go negative 4 and 2. So I'm going to go negative 4 minus, and notice I'm using parentheses also on that second number. kind of important when we're dealing with negatives. Later, most of our problems are all positive values, so it'll be nice. So 3 minus a negative 7 is the same thing as 3 plus 7. And negative 4 minus 2 is the same thing as negative 4 minus 2. So the top number is 10, the bottom number is negative 6, and it reduces to negative 5/3. So that's how you get to the negative 5/3 numerically rather than graphically. You should be able to do both, but the idea is pretty simple. Subtract the y's on the top, subtract the bottom as the x's, reduce your fraction. All right, so what if we want to graph a line from an equation? Well, whenever you're graphing a line, the only thing you really need is, well, of course, 2 points would be really nice, but generally a point and a slope. So as long as we can find a point and a slope, we should be able to draw a line fairly quickly. So when we're looking at y equals negative 2/3 x plus 4, it harkens back to this general equation of a line, y equals mx plus b. And the coefficient of x is the slope. So the slope of this line, which can be written as change in y over change in x, is equal to negative 2/3, because negative 2/3 is the coefficient, or the number sitting in front of x. All right, and then the b part is the y value of the y-intercept. So the y-intercept is going to be our point that we're going to need, and y-intercepts always start with the number 0. So it's 0, comma, whatever b is, and b in this case is a positive 4. So when we're talking about graphing a line from a point and a slope, it is important that you plot the point first. Slope doesn't plot anything. It's just a motion from the point. And then work with the slope. So we're going to go to 0, 4. Now remember, 0 means no left and right, and straight up 4. The other hint is a y-intercept has to be on the y-axis, not the x-axis. All right, the slope is negative 2/3. So if you separate it, it's change in y is negative 2, change in x is positive 3. So that means from the point I just plotted, I need to go down 2 and right 3. Down 2 because it's negative 2, and right 3 because it's a positive 3, and we can plot a point. All right, but we also could go the other direction. Instead of changing y as negative 2, we can make it a positive 2. But by doing that, we have to force the other number to be negative. So we would go up 2 and left 3 and plot a point. The 3 points line up rather nicely, and we should be able to draw a relatively nice line through them. So that is how you draw a line, given an equation and finding the y-intercept and the slope. Before I move on, one of the checkpoints that you should perform before you finish the problem is the slope here is negative. Make sure your line is going downhill as you move left from right. If you find that your slope is negative numerically, but your graph is going uphill left to right, you've done your slope, you graphed your slope wrong. It's just a nice little checkpoint. When we are looking for an equation of a line, and this part becomes kind of important for a lot of my problems, there are, well, technically there's only one method of doing it, but there's two varieties of problems that could be thrown at you. One of them will have a point and a slope, which is the, general idea of what a line is, and then the other one will give you 2 points. But when you're given 2 points, you use them and you come up with the slope, and you do it method number 1 anyways. So either case, you're eventually going to be looking for a point and a slope. So where the other equation of the line is really good for graphing it, and it's literally called slope-intercept, this one is going to be called point-slope form. So the point-slope form of the equation of a line is y minus y sub 1 equals m times parentheses x minus x sub 1. Now, when we're talking about x sub 1 and y sub 1, these two positions, this is literally the point. So you're given this point, and we're going to represent it by this x sub 1, y sub 1. And the sub 1 usually means first point. For instance, I didn't give it to you, but the formula for the slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I don't like that formula because people think that it has to be the second point minus the first point. And my whole idea, as long as you keep it in order, doing it the other way is perfectly fine too. So y sub 1 minus y sub 2 over x sub 1 minus x sub 2, and they're equal. So I prefer going left to right, so first point to second point. So this is just the representation of a point. The only other number in here is this m. The x and the y that aren't boxed are variables, and they just stay as they are. All right, so for example, let's say we want to find the equation of the line. Now, it's not of a line. When we have 2 points, it is a unique line that goes between them. So this is of the line that goes through these 2 points. Now, like I said before, this equation takes a point and a slope. So that second option is in play where we have 2 points, but we really need the slope first. So before we can even use my fancy equation, we have to find the slope. So to find the slope, we're going to subtract the y's over the subtraction of the x's. And in order, the y's are 7 and negative 5. So I'm going to subtract 7 and negative 5 over my x values in order. On the bottom are going to be negative 4 and positive 2, but I'm going to subtract them. So the top becomes 7 plus 5. The bottom stays negative 4 minus 2. We get 12 over negative 6, better known as negative 2. So the slope of this line is negative 2. Next up is, now we can use the equation. So you write it out. Y minus y sub 1 equals m times x minus x sub 1. All right, so I'm going to choose a point, and it doesn't matter which point you go from because it'll eventually get to the other point. So I usually just go with the first point. Sometimes it's best to go with nice numbers. It doesn't really matter. So it's going to be y minus something equals m times x minus something. I'm going to color code this so it looks a little prettier. So it's going to be y minus the, big mistake, y minus the 7, because y1 is the second coordinate. So this will be 7. And then it's x minus the first coordinate, which is negative 4. So I'm going to put that in parentheses. All right, and then simplify. So this becomes, up here, y minus 7 is equal to, oops, I forgot to put the m. Mistakes all over the place. What was the m? M is equal to negative 2. There, that looks better. And y minus 7 equals negative 2 times the quantity, and I'm going to simplify this. Negative negative makes it a positive. All right, so we can distribute the negative 2 and add a 7 across. But in this computer system, you can actually write this, and it'll mark it right. Personally, I like simplifying the whole thing. So this is going to become y equals negative 2x. This will give you a negative 8 plus 4, which will be minus 4. So the equation of the line in slope-intercept form is negative 2x minus 4, where negative 2 is the slope and 0, negative 4 is the y-intercept. So a bank offers 7% simple interest on a loan of $500. And what we want to do is find an equation that will find how much is owed based on a time frame of weekly. So the best thing to do here is to create coordinates that we can find slope, and then we can find the equation of the line. So one thing we're going to do is we're talking about how much is owed on this loan weekly. So I'm going to let this whole thing be represented by the future value. Then we, of course, have this $500. And we have this interest rate, but that is not really going to be a number we're going to use within our coordinate. So we're going to have to use that to find another point. So because the bank is offering this loan of $500, we're going to call that week 0 and then $500. Now, we have to determine independent and dependent so we can get the order of the points right. So since this formula is looking for how much is owed weekly, the F is going to go into the second location. So what's going to go in the first location is how we're going to find the future value, which in this case is based on time. So I'm going to put t over here. So this is the order of our coordinates. We're going to input time, and it's going to generate some future value. All right, so the first point, times 0, and our balance of $500. So to find another point, what we need to do is just pick another time. So any time's going to work, so you can use 1 week. I'm going to use 5 just to have a little bit of fun. So what about t equals 5 weeks? Well, to find out how much the future value is after 5 weeks, you have 2 choices of formulas. You could use simple interest, or you could use the future value version of simple interest. I'm going to go with simple interest because that's where most people would probably go. So I equals PRT. P, of course, is $500. The rate is 7%, so I'll write it as 7 over 100. And the time is 5 weeks, so that's going to be 5 out of 52. So typing that into a calculator, 500 times 7 out of 100 times 5 out of 52. So it's $3.37. So the interest is equal to $3.37. All right, so therefore the future value is the $500 plus the $3.37 for a grand total of $503.37. So what that gives me is another coordinate. And the other coordinate, let's do it in a different color. In terms of t comma f, we have to keep the order the same. The time is 5 weeks, and the amount of money in there is $503.37. Okay. So if I'm looking for the equation of a line that'll tell me the future value, I have 2 points now. So by what we were doing earlier, we're going to generate the slope. So change in. Now, again, this is important. It's always change in the dependent over change in the independent. So this is going to be change in f, which is in the y-coordinate spot, over the change in t, which is in the x-coordinate spot. So then we just subtract the f's and subtract the t's. So I'm going to go backwards, actually. I'm going to subtract in this order. So 503.37 minus 500, and you'll see why I do this in a second, all over 5 minus 0. So we're going to end up with the interest divided by the number of weeks. So the slope is the amount of interest earned every 5 weeks. Kind of cool. Okay, so if we change that to a decimal, 337 divided by 5. So about, I'm going to do the whole thing, 0.674. So this is 0.674. So now I can do the equation of a line. And remember, f is in place of y, t is in place of x. So we're going to get f minus f1 is equal to m is never going to change, that's the slope, times x in this case is t minus t1, and then plug in numbers. All right, so it doesn't matter what point you choose, but I highly suggest you choose the easiest of the points, which is 0, 500. And then we really don't even have to use this formula, but I'm still going to use it. So f minus, the f1 is 500. Just to remind myself to go up. So this is 500 equals 0.674 times t minus t1, and in that case it's 0. So this is going to give me f minus 500 is equal to 0.674 t, that's a 7. And then I'll have to add 500 across. So my final answer is going to be f equals 0.674 t plus 500. And then we can use this formula to find the future value, and it has interest built into it. So basically, you're earning 67 cents, or you have to pay 67 cents of interest per week. All right, so here's another problem that we could deal with in a linear fashion. My car gets 32 miles per gallon on a highway, and my tank holds about 12.5 gallons. So let's say we fill up my tank, and then we get in the car and start driving it. So I want to find an equation that will determine the amount of gas that is left in my tank after driving a certain distance. So let's start off with a few points. Well, one of the first things we have to do is, again, determine what's going to be the independent variable and what's going to be the dependent variable. And the clues are going to come from the question itself. So we're trying to find the amount of gas left in the tank. So that's going to be measured usually in gallons. So we'll call that G, capital G. And we're going to be finding this after driving some distance. Let's call that little d. So the order this is going to come in is I'm looking for how much gas is left in the car, and I know what distance I'm traveling. So when we're talking about an ordered pair, then the question is asking for how many gallons are left. That'll be your dependent variable. And the distance you drive is what's changing, and that'll be the independent variable. So the order of my points have to be D and G. Now, when we're talking about slope, it has to be change in gallons over change in distance. So that's important also, to know that it's gallons per mile rather than miles per gallon. And we'll see how that pops out when we do this. So the first coordinate I'm going to have, again, is going to be how many gallons do I have at the start of my drive. And since I filled it up, it's 12.5 gallons. So I haven't driven anywhere, I'm still sitting at the gas station, and in my car is 12.5 gallons. So that'll be my first coordinate. Now my second coordinate I'm going to create by driving. You could do 1 mile, but my suggestion is because the fuel economy is 32 miles per gallon, then why not drive 32 miles and see what happens? So again, in this order, D then G, distance in gallons, we're going to drive 32 miles. Now, if your car gets 32 miles per gallon and you drive 32 miles, that means you're using 1 gallon of gas. So the 12.5, we're going to reduce it by 1 gallon, and we'll be down to 11.5 gallons. Okay, and then we can find our slope. So down here where slope is, change in gallons, and it doesn't matter what order you subtract them in. I'll go this way. So change in gallons, 12.5 minus 11.5, of course, is the 1 gallon I chose. And then we're going to subtract 0 minus 32. So we're going to get 0 minus 32. So we're going to get 1 over negative 32. So the slope on this is negative 1/32. Generally, I like giving the negative to the top number. You don't usually leave it in the bottom. And I don't like sitting it out front like this usually on a fraction, because then you might run it into your fraction bar and lose the negative. So I like writing it negative 1 over 32 so the negative sign doesn't get lost. All right, so now we have slope and we have a y-intercept. So I'm going to do this a little differently. I'm going to do it right into y equals mx plus b. So this is slope-intercept form. And the reason I can use it is I have a y-intercept. So y in this case is g. M in this case is negative 1/32. X in this case is d. And then my y-intercept was 12.5. So this is the equation of how many gallons are left in the tank after I drive a certain distance. All right, for example then, um, what if I drove 300 miles? How many gallons of gas are left in my car? So the formula is G equals negative 1/32 times D plus 12.5. And this 300 miles is the distance, so it's going to go in place of D. So I'm going to put G equals negative 1/32 times 300 plus 12.5. Negative 1/32 times 300 plus 12.5. So we're going to have 3.1 gallons left if we just approximate it. Now, I did this earlier. I put 600 miles in there. And what happens is you end up with negative gallons, which doesn't make any sense. So there is another idea of when does the car run out of gas, and that becomes known as the x-intercept, well, in this case, the d-intercept. And also, the graph of the line looks something like this with negative slope. It has, 12.5 as a y-intercept, and then it's losing gas over time, and eventually it's going to run into the d-axis, and you have 0 gallons of gas. So this is what is known as a natural domain. The line is only in this portion, in the first quadrant. You have some gas, and then it goes down to 0, and you can't go extending the line to the left or to the right. So earlier, at the very beginning of this video, I showed you a graph that I found from the News of an Observer that showed the brand new number of cases per day, and I said that it kind of grew linearly. Now this is based off an idea called a scatter plot. Not all points are going to lie exactly on a line when we start talking about real life data. So scatter plots, basically, you have your x and y axis, and then you go around and you collect data. And because the world is strange, your data is going to be kind of spaced out. Now, if your data, kind of grows linearly, like if you could draw a line above it and below it, and the generalization of the pattern of points grows between these two lines, then we can consider this a linear growth type model. Then the other possibility is we collect all these points, but as time goes on, the points grow in this pattern. So if we tried to contain them within two lines, we're not containing a lot of these or a lot of these points. But if we contain them within two curves, exponential graphs always have this curve to it, then we would say that the model that we would want to fit to it is an exponential model. All right, so let me show you how this works in Google Sheets, and it'll find us an equation of a line that will be what's called best fit. What line goes between all these points so that like half of them are above it and half of them are below it. And the same thing for exponential models. It tries to find a curve and gives you an equation of the one that is closest to all of the points that are given. It's a neat little process. Thank God the computer is going to do it for us, because by hand it is a horrible thing. Opened up a Google Sheet and I went to the News Observer website and I downloaded the data they had for the 7-day average number of cases per day. When I look at this first number, 63, this is based on 7 days before this, so 318. So it would add 318 through 325, add all those numbers together and divide by 7, and the answer was 63. So you'll notice that the numbers are going up. That's not a good sign, but they're not going up drastically. So what I'm going to do, oops, I lost it, is I'm going to select all of these, both columns, including their titles. It's really important if you're going to do a scatter plot, make sure you give them titles up here so that when we do a chart, the computer kind of knows what to do with these things. So I'm going to go through and just select all of this information. To shift the picture. Then I'm going to come over here to where it says Insert Chart. Now, if it doesn't show up, like if your window is crunched, it'll be under the 3 dots. So it'll say More, and then you'll find Insert Chart. Expand this back out. That's good. All right, so Chart. Now, it's going to throw up here a line graph, which is all fine and dandy. All it does is connect all the points on the graph, but that's not what I'm interested in. What I'm interested in, so there we go. I lost my little side thing. So double click on the graph and you can see all the points are represented by these open circles, so it looks like a chain. But I don't want this type of graph. I want a chart style. So over here in the chart editor, in the chart editor, go to Setup, change this line chart because it's just a suggested one. And we want to go down here further to where it says Scatter. So I'm going to do a scatter plot. And the images are way too big for my liking. So I'm going to go to Customize. Oh, and make sure these 2 checks are checked here. Because if you lose one of them, you get these 2 lines that just go straight across the thing. So here by saying use column A as labels, it's talking about the x-axis. All right, so we're going to go to Customize. We're going to go to Series. We're going to change the size of that point to be as small as possible. I'd really want 1 in there. Let's see if it'll do it. All right. And you can choose a different shape if you want. You can do little stars or whatnot, but I like circles. So this is what's called a scatter plot. It's not exactly on a nice line, but the computer's going to find out exactly what line fits it best. So we're going to go to Series, and we're going to come down here to where it says Trend Line, and we're going to click that. And then we're going to choose linear. It should automatically be chosen. And the other one we're going to play with later is exponential. Though I don't know why I didn't draw it. That's weird. But I want linear. And I want a label, and we're going to use the equation. So it'll put the equation, it'll line up here. So it's y equals 16.3 times x minus 716,000. All right. Now, basically what this line is telling us how many cases it's going up per day. So if you had 10 cases on day one, day two is going to have 26 cases. Day three is going to have 42 cases, 42 cases. That's how the line of best fit is found using a spreadsheet. It is much easier than doing it by hand.